Hello and welcome to a new edition of our PSI Physics series. In our last lesson, we learned about the parallelogram law of vectors and the resolution of vectors. We briefly saw that both can be used to determine the resultant vector. In this lesson, we shall go into the details of it and look at actual determination of the resultant of some forces. By the end of this lesson, you should be able to 1. Apply the cosine rule and the sine formula in calculations. 2. Determine the resultant of two vectors by the parallelogram method and by resolution. 3. Apply the parallelogram method graphically, that is, drawing to scale, and analytically, that is, by calculation. 4. Determine the quadrant in which a vector lies by using the components of a vector. 5. Determine the resultant of 3 or more vectors using the resolution method. I hope you remember in some of our previous lessons, we talked about how to represent a vector. That is, small letters will be represented in bold type. Example, small a. In writing, they may be shown as A with a dash under it. Vectors which are represented in capital letters will not be shown with arrows on top of them. Example, F, F1, F2, and F3 will denote vectors. The arrows on the sides of the triangles against which they are indicated will signify vector notation. Some writers may choose to put arrows on the letters F, F1, F2, and F3. What do you understand by the term the resultant of a number of vectors or forces which act at a point? The resultant of a number of vectors or forces which act at a point is that single vector or force to which they are together equivalent. It is that single vector having the same effect as all the vectors taken together. From the previous lesson, what methods are available for the determination of the resultant of a number of vectors? The methods available are 1. The parallelogram method. 2. The resolution method. Note that since the resultant is obtained from the addition of vectors, for two vectors we can use the triangle law of vector addition or the parallelogram method, which is a deduction from the triangle law of vector addition. The resolution method can be used to determine the resultant of two or more vectors. While in principle, we can use the parallelogram method for more than two vectors by grouping the vectors in pairs and determining their resultant until we end up with two vectors, whose resultant we finally determine. The repetitive method will be tedious and cumbersome for more than two vectors. It is therefore more convenient to use the resolution method in this case. The geometry of the diagrams involving the triangle or parallelogram method reveals that we can apply the parallelogram method graphically, that is, drawing to scale. We can also use methods of solving triangles, that is, calculation or analytical method, can be used to obtain the resultant by the parallelogram method. This will involve the use of the cosine rule and the sine formula. Thus, we can depict the methods for the determination of the resultant as shown. That is, in determining the resultant, we can use the parallelogram method. The parallelogram method can be done graphically, that is drawn to scale, or analytically by calculation. The second method that can be used in determining the resultant would be the resolution method. Let's now look at the cosine rule and the sine formula. Let's consider the cosine rule first. If we reduce a parallelogram to a triangle, we can solve for the side C of a triangle when the resultant C is required as a diagonal of a parallelogram. C squared equals A squared plus B squared minus 2AB cos theta. That is, in determining the resultant C, the cosine rule states that C squared equals A squared plus B squared minus 2AB cos theta. The sine formula. For the sine formula, a triangle of side A, B, and C. The sine formula states that A divided by sine A equals B divided by sine B equals C divided by sine C. Where, for example, sine A means the sine of the angle facing A. Now, let's look at how the graphical approach of applying the parallelogram method works. Given two vectors acting at a point O, represented as adjacent sides of a parallelogram, we represent the two sides of the parallelogram to scale and measure the angle between them with a protractor. We then complete the parallelogram and obtain its diagonal from the point O. We measure the length of the diagonal and convert it according to the scale to determine the magnitude of the resultant. The angle between the resultant and any of the forces is determined by measuring with a protractor. The methods are best illustrated with these examples. Example 1. Two forces F1 and F2 act at a point O, as in the diagram shown on the screen. Determine in magnitude and in direction the resultant of the forces using 1. The graphical approach of the parallelogram principle, and 2. The analytical version of the parallelogram method, and 3. The resolution method. In the graphical method, we would need a graph sheet for this work. You have to choose an appropriate scale. Suppose the big squares of the graph paper have sides 2 centimeters. We choose the sides of 2 squares to represent 10 newtons. That is, 4 centimeters equals 10 newtons. This means 20 newtons will be represented by 8 centimeters and 50 newtons by 20 centimeters. Therefore, with our ruler, we draw a line OA A of length 8 centimeters to represent F1 equals 20 newtons. And with the protractor, we obtain another line OE, more than twice the length of OA, and making 60 degrees with OA. This will be like this. Along OE, we obtain B so that OB equals 20 centimeters. Using a ruler or a pair of dividers, we get this. Therefore, with OA and OB as adjacent sides, we obtain a parallelogram. This means AOB are three vertices of a parallelogram. We thus obtain a fourth point C, such that OA is parallel to BC and AC is parallel to OB. The sketch may look like this. This is because opposite angles of a parallelogram are equal and adjacent angles are supplementary or add up to 180. Now draw the diagonal OC of the parallelogram OACB and measure its length. This, according to the parallelogram principle, represents the resultant of the two vectors represented by OA and OB. The diagonal OC will be found to measure 25.2 centimeters. We thus convert it into newtons as follows. 4 centimeters equals 10 newtons, which was the scale we used for the graph. This implies that 25.2 equals 25.2 times 10 divided by 4, and this gives us 63 newtons. That is the resultant force. When we measure the angle between OC and any of the forces represented by OA and OB, we find that the resultant is about 63 newtons, making an angle of 45 degrees with the 20 Newton force, which is represented by OA, or making an angle of 15 degrees with the 50 Newton force represented by OB. Thus, in a diagram, we can have this. Well, this is what we get from the graphical method from the parallelogram principle. Let us look at our graph sheet. Can we now try the calculation or analytical method from the parallelogram principle? From the cosine rule, the resultant of F1 and F2 is obtained as the diagonal of the parallelogram and is the force F. Now, F squared equals F1 squared plus F2 squared minus 2F1 F2 cos theta. Note that theta is the angle facing F. This implies that F squared equals 20 squared plus 50 squared minus 2 times 20 times 50 times cos 120. This gives us 400 plus 2500 minus 2 times 20 times 50 times minus 0.5. This equals 2,900 plus 1,000, and that's equals 3,900. The square root of this value gives us F equals 62.4 newtons, which gives us the resultant force. The angle between F and F2, that is the 50 Newton force, can be found using the sine rule as follows. Using the diagram, from triangle OBC, 62.4 divided by sine 120 degrees equals 20 divided by sine alpha. This implies sine alpha equals 20 times sine 120 divided by 62.4. This equals 20 times 0.866 divided by 62.4. This gives us 0.2776. When we find the sine inverse of this, we get alpha equals 16.1 degrees. Thus, the resultant is 62.4 newtons, making an angle of 16.1 with the 50 Newton force, or making an angle of 43.9 with the 20 Newton force. It is observed that the answers are not the same as in the graphical method. The calculation method may yield more accurate answers in most cases, since there may be some small errors in measurement of length and angles in the graphical method. Now, let us turn to the resolution method. We can take one of the forces as a reference line and resolve along, example, the x-axis and perpendicular y-axis to it. For convenience, we can align the forces so that one of them lies either along x or y-axis. Letting the 50 Newton force lie along the x-axis, we have the situation as shown on the screen. Resolving along and perpendicular to the x-axis, we have F1 equals 20 cos 60 and 20 sine 60. F2 gives us 50 and 0. Note, there is no need to say that because F2 makes angle 0 degrees with the x-axis, the component will be 50 cos 0 equals 50 and 50 sine 0 equals 0. A vector of 50 along the x-axis has an x component of 50 and no component along the y-axis. In the same way, a vector of 50 along the y-axis has no component along the x-axis and a component of 50 along the y-axis. The components of the vectors lying along x and y-axis are as indicated on your screen. Let's now continue our solution. Resultant F equals F1 plus F2. This equals 20 cos 60 and 20 sine 60 plus 50 and 0. This gives us 20 times 0.5 and 20 times 0.866 plus 50 and 0. This gives us 10 and 17.32 plus 50 and 0. Thus, the components of f would be equal to 60 and 17.32. F can be represented as shown in the diagram on the screen. Note that signs attached to the figures in the vector in component form shows a quadrant in which it lies. Both 60 and 17.32 have positive signs, and the vector lies in the first quadrant. See the diagram on the screen to see the 4 quadrants labeled and with the signs of both components corresponding to each of the quadrants. Thus, continuing, we obtain the magnitude of the resultant f, whose component we have indicated. By the Pythagoras theorem, f squared equals 60 squared plus 17.32 squared. This equals 3,600 plus 299.98. This gives us 3899.98. The square of this gives us 62.4 newtons. Now, tan theta equals 17.32 divided by 60. This gives us 0.2887. Finding the tan inverse of this gives us theta equals 16.1 degrees. Since f makes an angle of 16.1 degrees with the x-axis and f2 equals 15 newtons has been placed along the x-axis, it follows that the resultant f equals 62.4 newtons and makes an angle of 16.1 degrees with the 50 Newton force, or 43.9 degrees with the 20 Newton force. I hope you have followed the lesson well and will be able to apply the concept to another problem. Let's now determine the resultant of 3 forces. Determine by the resolution method only the resultant of the forces as shown on the screen. In components, the 10 Newton force is 10 cos 30 and 10 sin 30. This equals 10 times 0.866 and 10 times 0.5. This equals 8.66 and 5. In components, the 5 Newton force is negative 5 and 0. The 15 Newton force is 0 and negative 15. Thus, the resultant F will be equal to 8.66 and 5 plus negative 5 and 0 plus 0 and negative 15. This gives us 3.66 and negative 10. Note the signs attached to the components. F can be shown as, from the diagram, F squared equals 3.66 squared plus 10 squared. This equals 13.3956 plus 100, giving us 113.3956. The square of this gives us F equals 10.6 newtons. For the angle, tan theta equals 10 divided by 3.66. This gives us 2.7322. Taking the tan inverse of this, we get theta equals 69.9 degrees. Thus, the resultant is 10.6 newtons, making an angle of 159.9 degrees. That is 90 plus 69.9 with true north. Thus, the resultant would be 10.6 newtons, 159.9 degrees. Note that here, because the three vectors or forces have been clearly specified with respect to the position in the coordinate plane, we can also specify the position of the resultant. That is, specify the direction using bearings. This is unlike the previous two problems in which the vectors were given and we were to determine their resultant. The direction of the resultant was specified by stating the angle it makes with the forces given. We could not have used bearings to indicate its direction. Let's remind ourselves on some of the things we've done in this lesson. We learned about the resultant vector and how it is determined using the parallelogram method and the resolution method, which we first met in lesson 5. We discussed the graphical approach to the parallelogram principle and looked at the cosine rule and the sine formula as methods that go together to determine the resultant analytically or by calculation when we are interested in using the parallelogram law. We also, in this lesson, looked at the resolution method of determining the resultant. Now take down the following questions and try them at home. Determine in magnitude and in direction the resultant of the forces shown on the screen. You can use this answer to check your solution. Resultant would give you 36.6 newtons, making an angle of 43.1 degrees with the 70 Newton force, or 106.9 degrees with the 50 Newton force. Well, this is where we would end today's lesson. Though it was a bit tough, I hope you loved it. So we'll meet for the next lesson. Goodbye.